So last class we were talking about balancing chemical equations and predicting chemical equations. This is part of why we learned all that nomenclature, just so that we could solve problems like this, and also just so we're familiar with chemicals a little bit, just a little bit. So I said we would start off on this problem last class, so we wanted to write a balance equation for the reaction of aqueous lead-2 sulfate with aqueous potassium iodide. We've got our keywords to form, meaning that we're now talking about products, solid lead-2 iodide, and aqueous potassium sulfate. So starting off with our reactants, we've got lead-2 sulfate. The 2, remember, with Roman numerals, meaning that we've got Pb2+, and sulfate, the ATE ending, indicating that it's one of our oxyanions. The one that we would memorize or the one that we'd find on our green sheet. So it's SO4 2-, and we can probably see that we've got a 2+ and a 2-, and so those will go together in a 1-to-1 ratio. So PbSO4 is our first reactant, and it's aqueous. We are also reacting potassium iodide. Potassium has the symbol K. It forms a 1+ ion because it's an alkali metal. It's in the group 1A. And we've got iodide, the IDE ending, indicating that it's negatively charged and that it's monoatomic. So it's just the iodine ion. It's not IO3- or something like that. And it's a 1 negative charge because it's a halogen. It's a 7A or group 17. And these will also go together in a 1-to-1 ratio. And it's also AQ. It's dissolved in water, aqueous. Then on the product side, we've got lead-2 iodide. So what we've done is we've swapped our negatively charged ions. So it's now going to be the lead-2, but with the iodide. So Pb2+ and I-, we can crisscross these, and we'll get PbI2. And this is a solid. And then our other product is potassium sulfate, which is our K+ paired with our SO4 2-. So this one will also crisscross to figure out that we have K2 SO4. And this one is aqueous. Okay, now that we're done with the first step, we've got our skeletal equation. It's not balanced. And this is the type of equation where we've got everything in one thing on both sides. So each of our chemicals, our lead is in one compound on both sides. Our sulfate is in one compound on both sides. Same for our potassium. Same for our iodide or our iodine. And so the way that I like to solve these is we find something that's different. So on our product side, we can see that we've got 2 iodines, we've got 2 potassiums. We can start with either of those. Iodine comes first, left to right. So we'll do that one. So we've got 2 iodines on the right side. We've got 1 on the left side. To get those to balance out, we need a coefficient of 2 in front of our potassium iodide. So now our iodine is all balanced out. Our I's are balanced. The other thing that we changed when we balanced our iodine is the potassium. So we're going to balance that next. So we've got 2 on the reactant side because we just added this coefficient of 2. And we can see on the product side we also have 2. So those are already balanced, nothing to change. And usually with this type of problem, when you reach something that's already balanced, that means everything else is balanced. Not always, but sometimes, frequently for this class especially. So now we can go look at everything else. So we've got 1 lead on both sides. So our Pb, 1 and 1. And our SO4 group, we've got 1 and 1. So this is all balanced up. So really the hard part was coming up with the names, getting the skeletal equation. The balancing part, pretty straightforward. hopefully. Questions? Great, one for you to try, balance the chemical equation. You're starting with a skeletal equation, so if you are not up to date with your nomenclature, that's fine. So go ahead and give this a balance. All right, so for balancing this one, this is the more common type of reaction that we're going to balance. So we can follow the rules that we learned last class, for how to balance these. So we're looking for something that's in one compound on both sides. Hydrogen is in HCl, it's also in H2O, so that's in one thing on both sides. We've got chlorine. Chlorine's by itself on the right side, so it's not in a compound, it's just chlorine. Oxygen is also by itself on the left side. It's not in a compound, it's just in the compound on the right side. So that means that we can change the amount of oxygens and chlorines without adjusting anything else. So we can move those up and down freely. We should balance our hydrogen first. So to balance our hydrogens, we've currently got 2 hydrogens on the product side, and we've only got 1 hydrogen on the reactant side, so we're going to need to get those numbers up. So if we had a coefficient of 2 in front of our HCl, that'll get our hydrogens balanced. And now we can balance whatever else we want to. So let's check our chlorines. On the reactant side, we've got 2 in front of our HCl, so that means we've got 2 chlorines. We also have 1 Cl2 on the right side, so we've got 2 chlorines, so that's already balanced. And then the last one to check is our oxygen, and for our oxygen, we've got 2 on the reactant side. We also have just 1 on the product side. So what to do? If we change the number in front of our H2O on the right side, that's also going to affect our hydrogen. We can do that. It's not the fastest way to solve the problem, though. It might feel like the most intuitive. It's not the best way to solve this problem. So we want to adjust the O2 because it's by itself and it's not going to change anything else. So the way that we get 1 oxygen on the left side is adding a 1/2 coefficient in front of our O2. And we're just going to have this here for a little bit because we can't have a 1/2 O2. We can't leave that there. We can't solve it this way. We're not done yet. We have to get rid of that 1/2. But with the way that it's currently written, everything's balanced. Since both sides are balanced, if we double both sides, that'll bring all the numbers up at the same time, and it's not going to throw it out of whack. It's not going to unbalance it. So our last step is to multiply all of our coefficients by 2, and this will get rid of this 1/2 that we just wrote in. But it won't upset the balance between the left side and the right side. So we'll end up with 4 HCl plus O2 goes to 2 H2O plus 2 Cl2. Any questions or confusions? Cool. So now we'll talk about some different types of reactions. There's a bunch of different ways that we can categorize the reactions. These are just a few of them. We're going to learn 4 basic categories of reactions. We're going to learn combination, also called synthesis, decomposition. These two are kind of paired. We've got also single replacement and double replacement. Replacement is sometimes called displacement instead. We're also going to learn a couple of specific types of reactions. Our first up is combination reactions. A combination reaction is just combining two or more substances into one. Also sometimes called a synthesis reaction. So you might see that occasionally. And the general format is that we've got something A reacting with something B, going to something that's got both of them in it. These could have subscripts behind them. They could have coefficients. The general idea is that we're taking two things that are separate, we're putting them together, and now they're together. So sodium metal reacting with chlorine gas is an example. So the Na and the Cl2 react, and it forms NaCl. Notice that we've only got one product. So two reactants, or more. It could be 3 or 4. It's more common that it's 2. And one product. There's probably some that have like 3 reactants, but the basic idea is that we're just lumping them all together, throwing all our ingredients together to make one product. So those are combination or synthesis reactions. We also have the opposite process. That's why I said that these are sort of paired. We also have decomposition reactions. So these are breaking up or decomposing one thing into multiple things. So we've got one reactant and multiple products. Typically, decomposition reactions involve the input of energy, heat, light, electricity, something to break the bonds in whatever our chemical is. So carbonic acid decomposes CO2 and H2O, which is an example of a decomposition reaction. It could also have 3, could have 4 products. In this case, it's just 2. 2 is more common, I think. So we've got combination reactions, decomposition reactions, and their opposites. We also have, as a specific type of reaction, a combustion reaction. A combustion reaction, you can think of this as burning. So when you're burning stuff, you're doing a combustion reaction. In a combustion reaction, a substance, some sort of fuel, reacts with oxygen, and it produces heat and light, and there's also some common products depending on what you're burning. So if you're doing a combustion reaction and your substance contains carbon and hydrogen, or carbon, hydrogen, and oxygen, then we're going to get out CO2 and H2O as our products. So for example, if you're grilling either inside or outside with methane or propane, outside you're typically using propane fuel. That's going to combine with O2 in the air to form carbon dioxide and CO2. One of the reasons that you should have some ventilation when you're cooking is because of the CO2 that's produced. And the propane is the C3H8. And you can see our products are CO2 and H2O. So a combustion reaction, we're getting a reaction with O2 from the air. If you've ever tried to start a fire and you just like threw a bunch of stuff together and you try to light it, you don't have very good airflow. Somebody might come along and say, hey, we need to spread these logs out so we can get some airflow in there, or you start, you fan it a little bit, give it some air, give it some gas to let it go. That's the O2. So it reacts with O2 to produce CO2 and H2O. Cars also do this combustion reaction. They produce CO2 and H2O. So if you've ever been behind a car at like a light, especially if you just got off the highway and you see a bunch of water pouring out of their exhaust, that's where this H2O comes from. That's where the water came from that's pouring out of their exhaust when they stopped at a light. So an example of a combustion reaction, octane is a component of gasoline. Write the skeletal equation for the combustion of octane, then balance the equation. So we're told that we've got octane, C8H18. And we would have to fill in the rest based on what we know about combustion reactions. So we know the combustion reactions involve the reaction with O2. That's why your car is an air intake. one of the reasons your car has an air intake. And then on the product side, we've got CO2 and H2O. This, of course, only applies to gas cars. So that would be our skeletal equation. We would have to know that we've got O2 as a reactant and CO2 and H2O as products. So all three of those parts we'd have to know, and then we go about balancing it. So we're going to look for something that's in one compound on both sides. We've got two things that fit that description. We've got carbon on the left and on the right in our octane and in our CO2. We have hydrogen in our octane. It's also in our water. So we can balance either of those first. I'm going to start with carbon. We've got 8 carbons on the left in our octane. We've got 1 in our CO2 on the right. To get those numbers to match up, we need a coefficient of 8 in front of our CO2. And then for hydrogen, we've got 18 on our reactant side. We currently have just 2 in our H2O on the right side. So to get that up to 18, we have to multiply by 9. So if we put a coefficient of 9, now we've got 18 hydrogens on both sides. And then the last thing to balance is our oxygen. We saved our oxygen for last because O2 by itself means that we can adjust that number up or down as much as we want. It's not going to affect anything else. So on the reactant side, we've got 2. Product side, we've got 8 times 2. So that's 16. And we've also got another 9 from our H2O. So we've got 25 on the product side. How can we turn 2, what can we multiply 2 by to get 25? $12.5, or in fraction form, 25 over 2. So we do 25 over 2. The 2 that we have here in our subscript cancels out the 2 that we've got in the denominator, and our 25 is left over, so we've got 25 oxygens. It's the same as 12.5. You could write that too, or instead. But we've got a problem, because we can't have half an oxygen, so what do we have to do? I think I heard it. Multiply everything by 2. So we'd have 2 C8H18 plus 25 O2 goes to 16 CO2 plus 18 H2O. And since everything was balanced before we multiplied by 2, everything should still be balanced after we multiply by 2. Although I somewhat frequently, not on these types of problems, but on redox reactions, which you'll learn about in Chem 1, I frequently forget to multiply stuff, so it's always a good idea to check. So that's an example of a combustion reaction. Questions about that? All right, other types of reactions. So we had talked about combination, putting things together. We talked about decomposition, separating things. We also have single replacement reactions. So a single replacement reaction is swapping one element in a compound. So these generally have the form where we've got something by itself, and we've got two things together, and A says, actually, I'm going to take your place, B, sorry, and we've got A, C, and B. So our one compound that we had, one of the members got switched out. An example of that would be zinc reacting with hydrochloric acid. So zinc reacts with HCl, and the zinc and the chloride get together, the H2 says, I'm going to dip, see y'all later, as gas. So replacing or switching or displacing one element would make it a single replacement reaction. If one wasn't good enough for you, we also have the double replacement reaction. So this is more like a do-si-do, hoedown sort of swap your partner sort of thing. So we've got a double replacement reaction, and in these, our positive and negative ions are going to swap and form new compounds. So what's happening is AB and CD swap partners. So we're swapping our B and D. So A, instead of being paired with B, is paired with D. C, instead of being paired with D, is paired with B. So we've got two things that are being swapped. Instead of just one thing. And we also have a specific type of double replacement reaction that's called a precipitation reaction. In our precipitation reaction, we have two aqueous solutions, so two things that are dissolved, maybe two clear liquids. We mix them together, and out of that forms a precipitate. And a precipitate is defined as an insoluble solid ionic compound. So we're mixing two liquids together, or two things that look like liquids together, and we're getting out a solid. Two things that are soluble, we get out something that's insoluble. The way that we predict single and double replacement reactions is we have to look at what type of chemicals we have. I think single replacement reactions are honestly a little bit more tricky for students in my experience than double replacement reactions. So we'll look at some double replacement reactions. We're involving one element substituting with another to generate new products. And so what we have to look for is which of the two things in our compound is our lone element or lone compound most similar to. So what kind of thing is Ca? Ca is calcium. What kind of ion does calcium form? It's a metal, so it's going to form a 2+ ion. So when it's reacting with FeCl2, the calcium is going to swap out for the positively charged ion, which is going to be the Fe2+. So calcium here would swap out for the iron. So then we would expect to have calcium chloride as one of our products, and we would have iron by itself. So we're switching out the metals in this example. In the second example, we've got MgBr2, magnesium bromide, reacting with fluorine gas. What kind of thing is fluorine? Calcium was a metal, formed a positive charge. Fluorine is a what? Nonmetal, and it's going to form F-. So in our compound, MgBr2, which of these two is also a nonmetal and forms a negative charge? Is it the magnesium or is it the bromine? It's the bromine. So our fluorine is going to swap in for the Br2. So our products will be MgF2 plus Br2. And in both of these cases, they just happen to be the same charge or the same negative charge. That won't always be the case, so sometimes there will be some balancing that we have to do with the reactions as well. So in this one, nonmetal swaps nonmetal, or anion swaps anion. So that's single replacement reactions. So you have to identify what is our thing that's by itself and which of the two in the compound can it swap out for. Is it a metal? Is it can it form a cation? It'll swap out the thing that comes first. Or is it a nonmetal or an anion and it's going to swap out the second thing? Double replacement reactions, we're just always doing the same thing. We're just swapping the anions or the cations, technically. It doesn't really matter which one you do, but I talk about it as swapping anions, so the negatively charged ions. So when we are doing double replacements, we're going to swap our anions between two ionic compounds. So we're going to have a metal, nonmetal, or a cation and an anion. And we're going to want to separate each of our ionic compounds into the positively charged ions, the negatively charged ions. And then we're going to swap the negatively charged ions, the anions, and put them back together. For example, we want a balanced reaction for barium nitrate and potassium hydroxide mixing. And we're just going to assume that a reaction occurs. So barium nitrate is BaNO3, potassium hydroxide is KOH. And these are going to undergo a double replacement reaction. So we need to figure out what our individual ions are. So we've got barium. Barium forms a 2+ ion. We've also got nitrate, NO3-. Our other compound, we've got potassium, which is K+. We've got hydroxide, OH-. And then we're going to swap just the anions, so the negatively charged ions. And I'll rewrite these over here on the right, and then we'll put them back together. So we've got Ba2+ and OH-. We've also got K+ and NO3-. And then we're going to put these ions together as our products. And we do need to swap and drop our crisscross this 2 from barium to the hydroxide to do that. So we're going to have Ba, and we've got 2 hydroxides, so we need parentheses around the hydroxide, so BaOH2. The other one, we've got a 1+ and a 1-, so those go together 1 to 1. So it's just KNO3. So again, all we did, I sort of skipped the nomenclature part at the front end, but we figured out what we were starting with, both of our starting solutions. We separated them into their ions. So we've got barium 2+, NO3-. We did the same thing for our KOH. We swapped our anions, our negatively charged ions, to look at new pairings of ions. So we've got the barium now with the hydroxide, the potassium with the nitrate, and then we recombine these into their neutral compounds, the formula unit BaOH2 and KNO3. And that's to get our skeletal equation. Now the last thing to do is balance. Do we have any questions before we balance? Okay. So for balancing these, we're looking for what's different. We've got hydroxide that's not balanced. We've got nitrate that's not balanced. Nitrate comes first, so let's balance that one. We've got 2 on the reactant side, 1 on the product side. The 2 are in the BaNO3 The 1 is in the KNO3. And to get those to match, we'll need a 2 in front of our KNO3. When we do that, we're also affecting the amount of potassium that we have. So we'll balance potassium next. We've got 2 on the product side because of that 2 we just put in as a coefficient. And we've only got 1 on the reactant side. So to get those to balance out, we need a coefficient of 2 in front of our KOH. That'll bring our potassium count up to 2. It'll also change our hydroxides. So now we've got 2 hydroxides on the reactant side. So OHs, we've got 2 of them. On the product side, we also have 2 hydroxides. So that's already balanced. This usually means that we're done, but we'll check our last thing just to be safe. So we've got barium, 1 on the left, 1 on the right. So our barium is balanced. So we have a balanced reaction. All right, this is our last slide for the chapter. I'll give this to you so you have a chance to try a double replacement reaction. All right, if you were stuck on getting started, we'll give you the starting materials. So rubidium hydroxide, one of our reactants. Rubidium is Rb, and hydroxide, we just have one of them. It's Rb plus, hydroxide's OH minus. And then our other reactant is cobalt 2 chloride. Cobalt being a 2 plus charge because of this 2 in parentheses. Chloride is a 1 minus, and so we'll have 2 of those. Okay, so now you can hopefully get started if that's where you were stuck. All right, so we've got our reactants from our nomenclature. Now we have to separate them out to figure out the new partner pairings. So we've got rubidium Rb plus, we've got hydroxide OH minus, cobalt CO2 plus, and the chloride, the Cl minus. And we are going to swap the negatively charged ions. So our new pairing is going to be Rb plus with Cl minus, CO2 plus with the OH minus. And to put these back together, for the Rb plus and the Cl minus, we can just put those back 1 to 1. So RbCl. For the cobalt and the hydroxide, we've got a 2 plus charge on our cobalt, so we're going to need 2 hydroxides to balance that out, so it'll be COOH2 with the hydroxide in parentheses so that we know that there's 2 of that whole unit. So that would be our skeletal equation. And then for balancing, we just need to look for 2 things that are not the same. So we've got 1 hydroxide on the left side, we've got 2 on the right side, so we can start with hydroxide. Again, we've got 2 on the right side, 1 on the left side, so we're going to need to bump this up. We can put a coefficient of 2 in front of our rubidium hydroxide to get our hydroxides balanced. When we do that, we also unbalance the rubidium. We change the rubidium, the Rb. So for Rb, we just got that up to 2 on the left side. We only have 1 on the product side, the right side. So we're going to need a 2 in front of the RbCl. When we do that, we also change the Cl. So now our Cl's maybe is balanced or not balanced. So we have to check. So our chlorides, we've got 2 on the right side. Oh, and look at that. We've got 2 on the left side. So we're already balanced there. And our last thing to check is our cobalt. So our cobalt, we've got 1 on the left side, one on the right side. So we're all balanced up. Questions? Yes?
Where did the second CO go? Like, I understand that you put a 2 in front of it after balancing it, but like when doing the reaction, where did the second one go? I don't know if that makes any sense.
So we had 2 chlorides on the left side, and where did one of them go?
Yeah.
So that's the balancing part, is to take care of that. We're just looking at how can we pair our ions together when we're putting together the products part. So don't worry about the coefficients, or sorry, the subscripts. When we're separating them and swapping them and putting them back together, don't worry about those. We'll figure it out in balancing. We'll edit that out in post. Other questions? Cool. That'll do it for chapter 5.